and welcome. So in this tutorial, we will learn to make a 2 by 2 multiplier using Verilog HDL, and we will simulate this Verilog code on this Xilinx software. So a 2 by 2 multiplier uh, has this circuit where we need a bunch of AND gates and half adder modules. So basically it has two inputs, each of 2 bits. So this is the first input and this is the second input, which is B, and the first input is A. So this circuit is obtained after this design procedure, which basically uh, implements the multiplication of the bits individually and then forms addition, right? So now let's move to uh, the Verilog coding of this module. So I have already made this project. So now let's add uh, source files. So first we will make this half adder module, which we will call HA, because as you can see in this figure, it this figure labels it as HA half adder, right? So first we will make this half adder module and then we will uh, complete this circuit using Verilog code, right? Let's click on the next and finish. So now you can write this code here. So this half adder module has two outputs, two inputs, basically requires two inputs A and B of 1 bit and two outputs, right? So now let's specify that A and B are inputs and S and C are output, right? So now we can write this two-line code for this half adder, where we first employ the XOR gate. So we write this S because sum is obtained by XORing A and B, right? And now uh, carry is obtained through the AND of A and B. So this is very simple. First, you specify the output, as you can see in both gates, and then you specify the inputs. If your inputs are more than two, then you specify the third input and fourth input, and so on. And these are the labels. So these labels specify the instance of these commands that you are using. So once you have made this half adder, now you need to simulate it. So just click on this simulation, click on this file, and now uh, click on this behavioral check. So as you can see, it is okay, there are no errors. So now we can move to uh, uh, the Verilog code of the 2 by 2 multiplier. But if you want to make a test bench for this particular module, you can go ahead, but I'm going to go and add another Verilog module, and let's call it multiplier 2 by 2, right? And so let's click next and finish. So now uh, let me, because now we are going to implement this circuit, so let's uh, put these uh, these files so that we can directly consult from this diagram, and we can implement it, right? So in this in this 2 by 2 multiplier, as you can see, there are two inputs. So the first input is A, it has 2 bits, and the second input is B, and it has also 2 bits. So let's say A and B, and it has so it has an output. So this output is the product, where C0, C1, C2, and C3 are the bits of the product. So let's call it product, prod. So now specify these inputs and outputs. So this this is how we specify sorry, 2-bit inputs, and then we specify 4-bit output, because as you can see, the product has 4 bits from C0 to C3, right? So we specify a 4-bit output like this. Let's call it, in fact, let it be P, and so P is the product, right? So now, we can directly start writing code. So as you can see, first we need to uh, use this AND gate, that AND gate between A0 and B0. So let's write this code. Let's let it be the instance be, let the instance be N1, and so the output. So, as you can see, the output of this AND gate is directly the first bit of the or the 0th bit of the product. So output in this case would be P0, and and the inputs here are A0 and B0, right? So we have multiplied the 0th bit of the or the bit of A that is on location 0, and this bit of B that is on location 0, and as a result we got this output which is C0 in this here, and we call it P0, right? So now we implement this operation where we have two AND gates and a half adder, right? So first we AND B1 with A0. So let's copy this. So we need two AND gates, so we copy it twice. So it's easier by copying, pasting, and changing inputs. But as you can see here, we have some intermediate gates, and each of these gates have some output. So we use wires uh, to store the outputs of these intermediate gates. So it is always easier to define wires on the go instead of defining wires beforehand. It is easier to define wires when as the need arises, right? So here we need two wires. So let's call this, okay, this wire W1. This is the output of this AND gate, and let's call this W2, which is the output of this AND gate, right? So W1 and W2. So these are our wires. Now we can specify this. So W1 is the output of the first AND gate, which is between B1 and A0. So A0 and B1. Again, verify it from here. So B1 and A0, right? And so in this gate, in this AND gate, we AND this B0 with A1, right? So let this be A1, and so the output of this AND gate is W2. So this is the second wire that we used. So let this be W2. Now we use this half adder module which we have already made. So HA and the label. So here we need to change the labels because we have already used this label N1, since we copied it here from here and then pasted here, so it is important that you change these labels. So that let this be N2 and let this be N3 and let this be N4. So so and then we specify the output. So we so this half adder module that we made has two outputs and two inputs. So so in this case the inputs are W1 and W2. So W1 and W2 are inputs, and so the output here is this the output from the sum side or the sum of this half adder is the first is a bit in the product at location 1, right? So let this be P1. So this is a bit from the product which is basically the sum of this half adder. So and this is at location 1. So this is how we specify this. And now this is the carry, and as you can see this is another intermediate output which is output of this half adder but input of the next half adder that we will use, right? So let's use another wire for this intermediate output. So let's call it W3, or maybe let's call it W3, right? So or you can also call it C, in fact, because let's call it C because it will help us remember that this is the carry from the previous half adder. So let this be C, and so here we are. So we have now implemented this part of this circuitry, and now we need to implement this one. So here we have this one AND gate and this half adder, right? So we use this AND command and specify the instance. Let's call it N5, and here again, so you need this wire, you need another wire that can store the output of this AND gate, right? So let's call it W3. So it's as I've already told you, it is always easy so to specify these intermediate wires on the go. So as you need a wire, you declare it and then use it, right? So W3, so this is the W3 wire that stores the output of this AND gate, and this AND gate has two inputs, A1 and B1. So A1 and B1. Right. Now we need to use another half adder, so we can use this half adder module that we made by simply following steps that we have been. So first we need to specify the instance, and then we need to specify the inputs or maybe output depending upon what you want to specify first. So it's easier for us to specify the inputs because one of these inputs is W3 and the other is the carry from the previous addition. So carry from the previous addition is C. So C is the other input. So once we have specified the inputs, now let's specify the output. So as you can see, both of the output of this half adder are bits from the product. So this is the sum, which is the second in fact which is a bit from at location 2 of the product variable. So let's specify this as P2, but this C3 is the C3 is the carry from this half adder, and it happens to be the final bit of the most significant bit of the product, right? So this the most significant bit of the product is P at location 3. So this is P3, and remember it happens to be the carry. So this is not, so this is the sum. So we specify sum here, as you can as you know from the half adder module, and this is the carry, uh, which which is basically the final bit of uh, this multiplication, right? So now we have successfully implemented this uh, 2 by 2 multiplier. Let's run its behavioral check. Click on the simulation, click on the file, and then click on this behavioral check. So there are no errors. So let's add a test bench to simulate it. So when we add a test bench, we select this Verilog test fixture, and let's call it. So this we name the test bench by uh, uh, attaching this test batch TB underscore uh, before the name of the module. So multiplier 2 by 2, right? So now we click on next, and we select the file that we want to link. So we want to link this multiplier 2 by 2, and then we click next, finish, and here we are. So uh, it has already defined the inputs, 2-bit inputs, a 4-bit output, that is product, and call to the function, uh, and now here we specify the inputs. So let's specify first input to be, so this A is a 2-bit number, so first we will specify the number of bits, which are 2, the type, which is binary, and then we specify the number, so let it be 10, and second we specify this to be 2b01, right? And in the next uh, instance, so we check the output of this multiplier on 2 different inputs, so let it be 1 1, and let this be 1 0, right? So these are the 2 inputs that we want to check the output on, and let's specify finish. So $finish. So this keyword finishes the simulation after these 200, the delay of 100 nanoseconds for this input, and then 100 nanosecond for this input. So basically the simulation will end after 200 nanoseconds, right? So now let's save this, click on simulation, which we have already done, click on the test bench module, and here you will see this ISIM simulator. Click on this behavioral check, and now click on the simulate behavior, and so the simulation has finished after 200 nanoseconds. So click on this default tab. So this is your simulation. Click on this zoom to fit button, and as you can see, this is the result. So when you multiply 10 by 01, this is the output 0010, and when you multiply this 11 with 10, so this is the output, which is 0110. So that's it from this tutorial.